Exponential and logarithmic equations. So up to this point, we've studied what exponential functions are. We've studied their inverses, the logarithmic functions, and we've developed properties for the logarithmic functions. In this section, we're going to be solving equations that involve these two classes of functions. Let's start with the following definition. An exponential equation is an equation in which the variable occurs in the exponent. And a logarithmic equation is an equation in which a logarithm of the variable occurs. So these two definitions are what you might think they are. Let's recall the following property. A correspondence or a relation or a rule f that takes input from D and outputs things in E, right? D is referred to as you remember, D is referred to as the domain of the function, and E is the codomain or the target set. Remember, the range of the function is a subset of E, right? At best, the range is E itself, right? Okay. So a correspondence f with that's defined on D with values in E is a one-to-one function if and only if the following holds. If x and y are the same in the domain, that's the same thing as saying that f of x, the image of x under f, and the image of y under f are also the same in the target space or target set E. Okay? And if you recall, this implication holds, the left to right implication holds because f is a function, and the right to left implication holds because f is one-to-one, correct? Remember, one-to-one means that no two distinct elements in the domain of the function have the same image, okay? Or equivalently, if you want, no element in the range is the image of more than one element in the domain, right? So left to right implication is because f is a function, and right to left implication is because f is one-to-one. Okay. All right. So next, we know that for a positive number a that's different than 1, the function a to power a real number and log base a acting on a positive entity, both of such functions are one-to-one, right? In fact, they are inverses of one another, right? As such, whatever you see, this property that you see above in pink, that property is going to hold for these type of functions, right? So in other words, if you replace f by a to power x, so a to power input, and if you replace f by log base a acting on an input, right? Obviously, the input here has to be positive because it has to be in the domain of the exponential function with base a, and we know the domain of such a function is R. We've learned it before. And the domain, I mean, whatever is going to sit here should be in the domain of log base a, and we know log base a do not act on numbers that are non-positive, right? So this guy has to be positive. Make sense? So I'm going to rewrite this statement here for one time for this function and one time for this function. And what do we get? We get exactly this, right? We get exactly this, these two. So given a number that's positive and different than 1, then ax equals ay. I'm reading this property from, I mean, it's equivalent, right? A statement is equivalent to another if and only if the latter is equivalent to the former, right? I mean, equivalence is reflexive. So it doesn't matter which one you state first. I'm going to state the left one first. Sorry, the right one here first, and then that's going to be equivalent to the left one. Okay? So that becomes ax equals ay if you take the function f to be the exponential function with base a. This becomes a to power x, and this becomes a to power y. And if these are the same, then you're gonna get that x and y are the same in the domain of the exponential function. And what's the domain of the exponential function? It's all real numbers. Similarly, if you replace f to be the log base a function, that's going to be read as log base a acting on x is equal to log base a acting on y. That's this side. And that's equivalent to x and y are the same in the domain of the function. And what's the domain of the log base a function? We've already said it. It's the set of all positive numbers. So x and y must be positive. All right. Let's employ these properties in some contexts. So let's go to the book. And this is 3.5. This is on page 416. And let's try to solve one of these equations from 5 to 16. Let's choose one. How about 12? So let's solve the following equation. 7 to the power 2x minus 3 is equal to 1 over 49 to the power x plus 1. Okay, so we're going to solve 7 to the power 2x minus 3 is equal to that. This is clearly an exponential equation because the variable occurs in the exponent. All right, so the base here on this side is 7. If I manage to rewrite the right side as 7, because it's the same base, to some power, then because of the property, the first property mentioned here, whenever this happens, that's exactly the same as the exponents are actually matching. Correct? Let's give this actually a name. How about we call this guy asterisk? And how about we call the second one double asterisks? Okay, so we can refer back to that. All right, so if we manage to write this side as 7 to some power, then I can match the two bases, right? A and A. As such, the exponents must be the same because of this property that we just developed, right? Which is true because, as we said, the exponential function with base A is a function that's one-to-one. That's why we have this property, right? All right, let's apply it. So 49, it's not hard to see that 49 is 7 squared, and 1 over 49 is 7 to the power negative 2, right? So this is 7 to the power negative 2. So then I get 7 to the power 2x minus 3, that's left hand side, equals 7 to the power negative 2. That's the 1 over 49, right? That's the 1 over 49. Why? Because remember the minus in the exponent? It means the reciprocal, right? The reciprocal of 7 squared, and the reciprocal of 7 squared is 1 over 49. And that thing is raised to power x plus 1, because I had x plus 1 here. Okay, so, and that's an exponential expression raised to some power. What do you do with the powers? You multiply them, and then you get 7 to the power 2x minus 3 is equal to, as we said, you multiply the powers. So you're going to multiply the negative 2 with the x plus 1. Okay. All right. And then because of property asterisk that we just talked about, and the bases match, it's the same base, 7. And that base is positive and different than 1. So asterisk is applicable, and as such, that's exactly the same. This is the important of it. You're not losing information along the way. You get an equivalent equation by just matching the powers, right? Just matching the powers. So this means by asterisk, that 2x minus 3 is equal to minus 2 times x plus 1. Does it make sense? And again, I can't emphasize it more. I mean, the important part is you transitioned from an exponential equation to, this is a linear equation, one variable, right? You transitioned without loss of information. That's the equivalent part. That's the importance. This is why asterisk is a powerful property, because it doesn't let you lose information, right? Okay, so, and that's equivalent. This is easy at this point. So 2x minus 3 is equal to minus 2x minus 2. So 2x minus 3 is equal to minus 2x minus 2. And if you solve this, solve for x, you get 4x. You get 4x is equal to 1. Am I correct? Because 3 minus 2 is 1. And that's the same thing as x equals 1/4, right? So what's the solution set? So the solution set is simply the set consisting of all the solutions. What are the solutions in this case? Just one guy, 1/4. So in this case, the solution set is simply a singleton, right? Okay. Okay, so, I mean, I don't know if it's needed to be explained. What this means is if you take x to be 1/4 in this thing, you replace x by 1/4, the two sides must be the same. Not only that, this is exactly, I mean, that's the only guy that does the job. This is why, this is the equivalence part, right? That's the only guy that does the job. There's no more than this guy. Okay. All right, let's keep going. Let's go to the book. Let's choose one from 17 to 34. Still, same question. Solve the equation, write the solution set with the exact value given in terms of common or natural logs. Okay. Forget about the approximation. Let's choose one. Which one you want to choose? How about 25? 25 is odd. How about 26? I'm choosing again an even numbered problem just because you don't have the answers to it. So 26. 5 to power, 5 times e, remember e Euler's number? 5 times e to power 4m minus 3. That product minus 7 is equal to 13. Solve for m. Okay, so let me zoom in. This is, as we said, this is number 26. 5 times e to power 4m minus 3, minus 7 is equal to 13. Okay, and we want to solve for n. Very good. So we want to undo all the actions that are done on m, right, in some sense. So there is m is multiplied by 4, and then that result is subtracted by 3, and then the exponential function with base e is acting on that, and then the result is multiplied by 5, right? We're going to undo it in the same order but backward, right? We're going to eliminate the 5, and then eliminate the e, and then eliminate the 3, and then eliminate the 4, right? To free the m, to solve for m. All right, let's get this out of the way first, the 7. And how do we get it out of the way? We want to add 7. If you add 7, you get 5 e to power 4m minus 3 is equal to 20, right? Because you add 7, you get 13 plus 7, which is 20. And as I promised you, we're going to do all the actions that are done on m, but in the reverse order, right? So we're going to eliminate the 4, eliminate the e, or undo the e, and undo the 3, add subtraction by 3, want to undo it, and then we're going to undo the multiplication by 4 at the end. Okay. All right. So that's the same thing as saying then, let's undo the action of multiplying by 5, which means dividing by 5 or multiplying by 1/5. We get e to power 4m minus 3 is equal to 20 over 5, and 20 over 5 is simply 4, right? And then, do you remember the asterisk property above, this one, which says that if ax is equal to ay, where a is the same base, right? The same base, and positive and different than 1. So if this happens, then this is the same thing as saying x and y are the same. Okay? So let's try to invoke this one here. You're going to tell me, oh, here I have the base e and here I have the base 4. And that's a very good question. But I can rewrite, let's say, I can rewrite 4 as e to some power. I can rewrite 4 as e to some power. And what is this power? Do you remember that the exponential function with base a and the log function with base a are inverses, so they undo each other if you put them back to back? So if you put this with this back to back, they undo each other, right? So if you put 4 here, since these are going to undo each other, that's going to be the same thing as 4 then. Correct? A log base a of x is simply x. Agree with that? As such, we've rewritten 4 as an expression with the base e. And that's what we wanted to invoke the asterisk property above, right? Okay. So this means that this is equivalent then to e to power 4m minus 3 is equal to e ln of 4, right? All right, now asterisk property kicks in. Now it kicks in. It kicks in with what? It kicks in with the base e to be a over there, and this guy here to be x, and this guy, right, this guy to be y, correct? Make sense? All right. So this means that 4m minus 3, the two powers must be the same, is equal to ln of 4. All right, and this is the same thing then. This is easy now. Don't worry about this. I know that this looks a little weird, but it's a number. Like square root of 2 or pi or whatever. This is a number. It's ln acting on 4. This is not a multiplication here. This is not a multiplication. This is an action, right? It's an action. So ln of 4, it's one number. This whole thing is a number. Okay, so you cannot don't think that dividing by ln, I mean, you cannot do so because, I mean, it doesn't make sense. It's not a defined operation. You cannot say, oh, I'm going to divide by ln. This is not a defined operation. Okay, so don't confuse this because ln is a function. It's not a number to divide by it, right? Okay. So I'm just throwing these wrong ideas. Again, I want to solve for m as I promise you at this stage, at the point. I wanted to undo the 5. I've done it at this stage. I wanted to undo the e. I've undone the e, right? No more e at this point. And now I'm gonna undo the 3 and then the 4, right? Okay, so how do you undo the 3? Well, by adding 3. And then you get ln of 4 plus the number 3, right? ln of 4, whatever this number is, it's a positive number, right? Whatever this number is, I added to 3. And that's 4 times the n. And this means that m is the fourth of that, right? It means the fourth of that. Correct? Don't cancel the 4 with the 4. Remember, ln is acting on 4, and this whole thing is a block. You cannot separate any of its pieces, right? ln is acting on 4 before it talks to this 1/4. So this whole thing has to take action. That thing is divided by 4 at the end, right? Okay, so what's m at the end? M is this number, whatever this number is. So that's the only m that does this job because of the equivalences that are going on, right? Let me show you a different perspective. Let me show you a different way or approach to actually handle such a thing here. So another perspective is I can rewrite this equation. As what? How about we invoke double asterisks? Maybe it's less visible, but look. If you have two numbers that are positive and they match, then you can apply log base a to to both sides and get an equivalent equation, right? One more time. If you have two numbers that are positive and they match, I'm reading it backwards, right? If you have two numbers that are positive and they match, That's equivalent to saying that log base a of x is equal to log base a of y. In other words, you can apply log base a to both sides and get an equivalent equation because the function is 1 to 1. Correct? You're gonna tell me, oh, what is a? Well, a can be any number of your choice as long as this number is positive and different than 1. It doesn't matter. I mean, you always pick up an equivalent equation, but you choose the one that's best suitable to your context. Okay? So I can apply to both sides log base a, and a can be chosen whatever fits best for me. I can choose any number that's positive and different than 1. I'm going to choose the one that simplifies my problem, right? And what is the one that simplifies my problem here? Again, I'm going to apply log base a to both sides. I'm going to apply log base a to both sides where a is still to be determined, right? It's still to be determined at this point. E for m minus 3 is equal to log base a of 4. Oops, sorry. Log base a of 4. The question is, what should a be? What should this guy be? Well, I want to choose it. I cannot choose it. I should choose it as a positive number and different than 1. That's for sure. But the question is, I have infinitely many choices. Which one should I choose? Well, I'm going to choose the one that undoes e. Why? Because I'm after m, right? I'm after m. I would like to undo the action that's done on this expression for m minus 3, and I'm taking the exponential, the natural exponential function here, right? E as acting on 4m minus 3. I want to undo the action that e, the exponential function with base e, is doing. And what's the function that undoes the action of e? It's the log of that base. It's the log of that base. So who should the base be? It should be the base e then, correct? It should be the base e. So if you take the base e here, that would be a good choice. Even though I was allowed to choose any base I want as long as the base is positive and different than 1. But I'm going to choose the base e so that they are back-to-back log base e acting on an exponential function with the same base, no action anymore, and then the 4m minus 3 is free. Correct? And what's log base e notation-wise? This is ln, right? This is ln. This is ln. Let me keep the equivalence going. So this is the same thing as ln of e to power 4m minus 3 is equal to ln of 4, right? Because log base e is denoted by ln. Sounds good? All right, and then ln back to back with e, as we just explained. They neutralize each other's action, and then you're left with 4m minus 3 here is equal to ln of 4, which is this stage. And then we can proceed exactly as we did before. Correct? So from here we can simply say that 4m minus 3 is equal to ln of 4, which at the end of the day we should get the same thing as we got over there, right? 1/4 ln of 4 plus 3. Does this make sense? So you get to choose the approach you want. They're all the same. They're equivalent. Yeah, whichever you desire to do. Okay. All right. So let's keep going. Let's try one more on this group here. How about so we've done 26. Let's do 30. Let's do 30. So 30. (11 to power 1 minus 8x is equal to 9 to power 2x plus 3. All right. This is clearly an exponential equation. clearly an exponential equation, but the bases are not the same. Here I have the base 11, here I have the base 9, and as such, the asterisk property doesn't apply, because we must have the same base for the property asterisk to be invoked, right? So I cannot do so. So what should I do? Well, how about we apply the thing that we just applied over here? How about we apply the thing that we just applied here, which was double asterisk, if you remember, right? It was double asterisk that we applied here. Remember, double asterisk means if x and y are both positive then this is going to be equivalent to log base a acting on one side equals the same log function, log base a, acting on the other side, right? This is the double asterisk above. Clearly here at the time I forgot to say that they're both positive, right? This is certainly a positive number. Exponential of base e doesn't produce a number that's 0 or less. This is certainly positive, and 4 is a positive entity. So that's why we applied double asterisk. Over here, same thing. This is a positive entity, and this is a positive entity because this is an exponential expression with the base 11. So that thing is certainly positive, and similarly that one. So we can apply double asterisks. As such, we get, let me stick with purple. So as such, we get, by employing double asterisks, that log base a, again, a is something to be determined, 11 to power 1 minus 8x is equal to is equal to log base a of 9 to power 2x plus 3. Okay, and the question is, what do you want to choose for this base? As long as you choose a base which is positive and different than 1, you're good, right? You get the equivalence. What's the best one to choose? Well, you might think 11. If you take 11, these two cancel each other, right? But log base 11, 9, back to back, they don't cancel each other. Okay, and if we go with the base 9, these cancel each other, but these two do not cancel each other. So it looks like there's no preference here. There is no preference. So what we're gonna do, you can choose whatever you want. I'm gonna choose E, base E. Again, there's no reason to prefer one in favor of the other. I'm just gonna go with the natural base, E. Okay, so I'm gonna erase these, and I'm gonna choose E. All right, which means this is gonna be ln. How about I rewrite it? So that's gonna be ln of 11, 1 minus 8x is equal to ln of 9 to power 2x plus 3, right? You're gonna tell me, oh, but ln doesn't cancel any of these two bases. I agree with you. However, it allows me to bring the exponent down. Remember one of the properties for logarithmic functions? I'm talking about this. Log base a of a to power c is equal to c times log base a of capital A, right? That's the property I'm alluding to, this one. So that's what I'm going to be needing. Correct? So on the left side, log base a is ln, capital A is 11, and capital C, the power, is 1 minus 8x. So I can bring this down as a coefficient, and I get 1 minus 8x times ln of 11, right? If you don't put these parentheses, look, if you don't put these parentheses, it means that the 8x is the one that's multiplied by ln of 11. But this is not what this property, the green property, is saying. It's saying that the whole c is multiplied by ln of 11, right? So the whole c is 1 minus 8x. And one more time, we're going to apply it on this side, and the 2x plus 3 this time is going to play the role of c. So we get 2x plus 3. The whole thing is going to be multiplied by ln of 9. Makes sense? Okay. And what's ln of 11? I know I don't know the number, but it is a number. This is a number, so this is one package. This guy is one package, and this guy is one package. I mean, here ln of 9, I can think about 9 as 3 squared. I can think about 9 as 3 squared. And I can bring the square, I can bring the 2 down, right? My point is, I can think about ln of 9 as ln of 3 squared. Correct? And I can re-invoke the green property and get the 2 down. Sure, I can do so. Make sense? Just to keep the 3 by itself. But again, what's the point? There's no point. Just keep it 9. The point here is to just solve for x, regardless how you're gonna represent that x. If you want to represent it with 3 as opposed to 9 here, I mean log is acting on 3 as opposed to 9, sure, take the 2 down. But if not, ln of 9 is the same as ln of 3 squared. If you just care about what the x is, this is good enough, the purple one, right? So I'm gonna just erase. I'm not gonna go through this run. Again, the point is, I don't see the point. Okay. So how do we solve this? How are we gonna solve this? Well, in the case where, I mean, remember, ln of 11, ln of 9 are both numbers, right? Whatever these numbers are. So what did we used to do when this thing used to be a better looking number, maybe? Like 7 or 8 or 9 or 5, whatever it is. So what did we used to do? Over here and over here. Most likely you're gonna say that we used to distribute the multiplication over subtraction on this side, and we're gonna distribute the multiplication over addition on this side, right? When we used to have better looking numbers, let's say. Okay, so that's exactly what I'm gonna do, because I mean this is no different than the others. This is still a number, but probably it looks a little weird, right? But it is a number. So we get that number times 1 is that number, so ln of 11, minus 8 times this number times x, right? Minus 8 times x times this number is the same as saying minus 8 times the number times x, because multiplication is commutative, right? So we get this. Remember, it's multiplication. So since multiplication is also associative, I can group these two together, and then the result is going to be multiplied by x. And then this is equal to, same story, 2x times ln 9. I'm distributing again this multiplication over this operation, plus. So 2x times ln of 9 is the same thing as saying 2 ln of 9 times x. And again, for the same reason, I can group these two together, because multiplication is associative, plus 3 times ln of 9. Makes sense? Plus 3 times this number. Okay, what am I doing? I'm after x. In this case, that's the coefficient of x, and in this case, that's the coefficient of x. Think about x as an image. This is how many images I have here, and this is how many images I have here. Don't worry about how the number looks like, okay? It's just a number. So, what did we used to do? How did we used to handle such an equation? What's the nature of this equation over here? It's not an exponential equation anymore. We're not at this point anymore, right? We transition to a stage, or to a level where we can handle using old techniques, right? Old techniques. This is of the form number times a number times x. Sorry, a number minus a number times x equals a number times x plus another number. This is a linear equation in one variable. So we used to bring all the x's together on one side and bring all the constant terms to the other side, bundle them up, right? And then divide by the coefficient that they're gonna pile up for x on this side, correct? So what we get is minus 8 times ln of 11 times x on this side. I'm subtracting by this. If you subtract by this to lose it from the right side, you get minus 2 ln of 9 times x equals 3 ln 9. And let's bring the other constant term here, which is ln of 11. So to lose it from this side and let it pop up on this side, we're gonna subtract by this number here. If you subtract, you gotta do it here. So minus ln of 11, right? Makes sense? I'm still after x. I'm still after x. Okay, so what do I do now? What did I used to do when this case was like 7x minus 3x? What did we used to do here? If this guy is 7 and this guy is 3. We used to subtract 3 from 7, right? And get 4x. So subtract 3 from 7 and get 4x. So we used to do this, which means what in this case? Which means factor out x and subtract these coefficients from each other, right? Obviously while respecting the order, correct? So I'm gonna try to inherit that technique to this less intuitive, let's say, less intuitive stage. Okay? So let's apply the same technique. I'm gonna factor out the x, and get minus 8 ln of 11 minus 2 ln of 9 as a I mean, if you divide this guy by x, which means factor out x, you get simply this quotient, right? Which is minus 8 ln of 11 and minus 2 ln of 9 if you do the same for the second term. All right, equals 3 ln 9 minus ln of 11. Okay? And whatever this number is, what I'm gonna do now, since I'm gonna undo its action, and its action is I'm multiplying by this number. To undo it, you just divide by this number, right? You just divide by this number. So you get x equals 3 ln 9 minus ln of 11 divided by negative 8 ln of 11 minus 2 ln of 9, right? Okay, bothered by this. Let me just fix the writing here. Okay, makes sense? So you cannot simplify again. You cannot simplify 11, 11, 9, or with 9 or whatever. ln of 11 is a package, right? ln of 9 is a package. You cannot even simplify by ln of 11 here and here. Why? Because ln of 11 is not a common factor downstairs and it's not a common factor upstairs to factor it out and divide by this, right? So what I can do, I mean, this is the answer. This is the answer, just to be clear. If you would like to have it, I mean, more simplified in terms of having less minuses, that's the best I can do. Simply reduce the number of minuses you might have. And what I can do to do so is to factor out minus 1 downstairs and minus 1 upstairs. And if you factor out minus 1 upstairs, you get minus 3 ln 9 plus ln of 11. And if you factor by minus 1 downstairs, you get 8 ln of 11 plus 2 ln of 9. And now if you simplify by the negative 1 and the negative 1, you simplify by negative 1 and negative 1, you get that x is equal to minus 3 ln 9 plus ln of 11 divided by 8 ln of 11 plus 2 ln of 9. Correct? So that's what you can get. Is this last step necessary to simplify? The answer is no, because you found the x. And this x and this x are the same, but this has a different writing than this, but value-wise they are the same. And I have no reason to prefer this in favor of that. Okay? So in conclusion, we obtain that the solution set is simply the set consisting of the solutions, and in this case there's one and only one solution, so it's the set consisting of my solution. What's the solution? It's this guy, correct? That's my guy. So this guy, I'm gonna copy it and paste it right there. Make sense? So that's the solution set. All right, let's keep going. How about now going to problems involving logarithmic equations? How about we answer number 36. Determine if the given value of x, three values, three parts, is a solution to the logarithmic equation. All right, let's do let's do all of them. Okay, let's do all of them. So 36. I have log base 4 of x equals 3 minus log base 4 of x minus 63. For part A, they told us replace x by 64 and check if that's going to be a solution. Well, replacing x by 64 amounts to writing log base 4 of 64 equals 3 minus log base 4 of 64 minus 63, right? What have I done? They told me to replace x by 64 in the sense that they asked if x is equal to 64 as a solution. So if x equals 64 is a solution for this equation, which means replace x by 64 and see if you get a true statement. All right. Okay, so the question becomes, are these the same? That's the question, right? And to answer this question, how about we simplify the left-hand side and the right-hand side and see if they match? Let's start with the right-hand side. What's the right-hand side? It's 3 minus log base 4 of 64 minus 63, right? And what's 64 minus 63? It's 1, correct? And what's log base A of 1? Whatever A is, as long as A is positive and different than 1. What is this guy? This is 0, am I correct? It's one of the properties we've learned in an earlier section. So log base A of 1 is 0. Okay, and that's, remember, I mean, the graph of log base 4 is something like this. Correct? And it crosses that, it's a one-to-one function. It crosses the x-axis one and only one point and happens to be at 1. So that's why you get this is 0, right? Okay. Okay, so and then what do we get? We get that the right-hand side is 3 minus the 0. And what's 3 minus the 0 is 3, right? 3 minus the 0 is 3. How about the left-hand side? The left-hand side is log base 4 of 64. Okay? And 64 is the same thing as 4, right? One more time. I'm trying to see if this guy is matching 3. I'm trying to see if this is actually 3. Correct? Is it true that 4 cubed is 64? Is it true that 4 cubed is 64? Well, 4 cubed is 2 squared to power 3. And 2 squared to power 3 is 64. Because 2 cubed is 8. squared is 64. So this is correct. And now we have log base a of ax. Log base a of ax. Remember, log base a acting at the exponential function with the same base. They undo each other, and what you only get is that exponent. So this is really 3, right? Because log base a of ax, back to back log base a and exponential function with the same base, neutral action, no action, output the same as this guy, 3. So right hand side and left hand side are the same. As such, x equals 64 is a solution of this equation, this logarithmic equation, right? Makes sense? So this is a solution. How about we write with green? Okay, which means it is a solution. Part B. Part B. Part B is we want to replace x by -1. We want to replace x by -1. If you replace x by -1, we get log base 4 of -1 equals, we don't even need to continue, right? If you replace x by -1, look, this guy becomes like this. Correct? We don't even need to check the rest, because what is that? This is nonsense. This doesn't make sense, right? Because log base 4 doesn't act on numbers that are 0 or less. Correct? It only operates on positive numbers. Remember the domain of log base a function? It only operates with on inputs that are positive. So this is not meaningful. That alone being a solution. So -1 doesn't only produce, is not only is not a point which is not a solution, it's also an entity which produces an error in the equation. It produces a non-meaningful equation. So it is a no, right? Certainly it's a no. Because, let's just say, since log base a of, in this case a is 4, right? Log base 4 of -1 doesn't make sense. Correct? All right. Part C. Part C, now x is given to be 32. Now x is given to be 32. So I'm going to replace x by 32 here and x by 32 here. And the question becomes, is log base 4 of 32 the same thing as 3 minus log base 4 of 32 minus 63? Correct? This would be the question. Okay? I hope you see the same problem here. Sure, this side makes sense. The left-hand side makes sense. But look at the right-hand side. This is a negative number, right? This is a negative number. What is it, like -31 or something? The point is that this is negative. Log base 4 doesn't act on a number that's 0 or less. It only operates on positive numbers. So this is not meaningful. This is not meaningful. So x equals 32 produce an equation which is non-meaningful equation, because one of the entities doesn't exist. It doesn't make sense. So as such, we cannot compare the two, right? The left-hand side is a number, but the right-hand side is not even a number. So I cannot compare it. Because to compare, both of them should exist and they should match. That's what comparing means. I mean, that's what equality means, right? Both of them exist and they should match value-wise. Since one of them doesn't exist, so I cannot compare, then they're not equal for sure. Okay? All right, so it's a no. So it's a no again, since log base 4 acting on 32 minus 63 is not meaningful, right? Okay. All right, right, let's keep going with the problems in the book. And let's choose one of these, or a couple of these problems. Let's start with about number 50. Log base 3 of y plus log base 3 of y plus 6 equals 2. Okay, so this is number 50. So we have log base 3 of y plus log base 3 of y plus 6 is equal to 3. Okay, so I want to solve for y. So I want to undo all the actions that are done on y. And obviously log base 3 is acting on y, or a variation of y plus 6, right? So what I'm going to do is I'm going to try to bundle these up. Look, log base 3 of y plus log base 3 of y plus 6. Can you condense this expression? Well, this is something we've dealt with in the previous section. The sum of logs with the same base is the log of the product, right? And the product here means y times y plus 6. So the log of a product is the sum of the logs, right? Is equal to 3. Okay. All right. And then what? Well, let me take you back to double asterisks. Where was that? It was here, right? You see this? Log base a acting on x equals log base a acting on y. Whenever log base a is acting on numbers and produce the same output, then and only then the two numbers must be the same. Correct? I'm gonna invoke that. I'm gonna try to employ this. Well, here I have log base 3 on this side, and this side it looks like I don't have the log function acting on anything. How about we rewrite 3 as log base 3 acting on something? Well, we know that log base 3 of 3 is 1, right? Log base 3 of 3 is 1. So if we multiply 3 by this green piece, it remains 3 because this is a 1, correct? Because this is a 1. Agree with me? 3 times 1 is still 3, so I'm not doing anything. All right, why this is useful though? Because now I can employ the following property. Log base a of a to power c is the same as c times log base little a of capital A. Remember this property? I'm going to use it now. I'm going to use it backwards. I'm going to use it from right to left. I'm going to use it from right to left. On the right hand side, I have c as being 3. I have little a to be 3 and capital A to be 3. So they're all 3 in this case. So what do I get? I get log base 3 of 3 cubed. Correct? So this becomes log base 3 of y times y plus 6 equals log base 3 of 3 cubed. Agree with me? And then at this point double asterisk applies. So at this point double asterisk applies, and what do we get? We get that the two arguments must be the same, and this is equivalent. This is equivalent. We get that y times y plus 6 must be 3 cubed. Correct? Let me show you a different way to actually pass from this stage to the stage, from this stage to the stage. Another perspective. Let's pretend, let's just isolate this piece, take it a little bit aside just to discuss another approach, and then I'll bring it back, okay? I'm gonna, over here, I'm gonna apply an exponential expression with a suitable base. Okay, what am I saying? I'm saying the following. I'm gonna apply asterisk, this property with a suitable base. Remember, property asterisk apply for any x and y real numbers. No matter what x is, no matter what y is, if you apply the exponential function with base a to both sides, you pick up this, you pick them up, that they are the same, and this is going to be an equivalent equation, correct? Which means you did not lose any information along the way. So let's take this and bring it down, this knowledge, and bring it all the way to this problem. So we have that thing as x, that's going to be the x of the asterisk, and that's going to be the y of the asterisk. Okay, so I'm going to apply this. I'm going to be very clear here. So I'm going to apply this with, so I'm going to apply asterisk with what? With log base 3 of y times y plus 6 as being the x of the asterisk, as being the x of the asterisk, and the y of the asterisk, I want to apply it at, I want to give it the role of 3. Correct? So this becomes x equals y, and by asterisk this means a to power log base a of 3 is equal to a to power 3. Correct? So by asterisk I can rewrite this as a to power log base 3 of y times y plus 6 is equal to, sorry about this little mess here, but you got the concept, equals to a to power 3, right? A to power 3. Correct? And the question is, remember, I have the choice of a. A can be any number as long as this number is positive and different than 1. Who am I going to choose a to be? Well, I'm going to choose a suitable a in the following sense. I want to undo the action of log base 3. Why? Because I want a free y at the end of the day. I'm trying to solve for y, right? I want a free y. So who that base should be to undo the action of log base 3? Oh, it's the exponential function of the same base that undoes it. Correct? So as such, a suitable a would be 3. A suitable a would be 3. Does it make sense? And if you choose such an a, what do you get? 3 log base 3 back-to-back neutral action. You get back y times y plus 6, which is what we got here, but via a different method, equals to 3 cubed, which is this side. Correct? So seeing it this way or seeing it this way, the good thing is in mathematics the answer is unique, so don't worry. As long as you're doing a correct step, you are in the right direction. Okay? All right, so the previous one, we use this. I promise you to bring it back. How about we bring it back? What should I do? How about this? Okay, something like this. I don't know, something like this. Anyway, so keep in mind when you revisit the notes that these are two distinct approaches, okay? So these are two distinct approaches. I'm gonna do this for you. Let me take this aside a little bit and just box this for you, just to indicate that this is a different approach, right? Okay, now let's take this back and put it here. All right. Okay, so we get to this point anyway, right? Once we get to this point, this is a quadratic equation. This is y squared plus 6y equals 27, which means this is y squared plus 6y minus 27 equals 0. All right, you factor it using quadratic equation or some intuition. This is not This is not hard to see. What is it? Y minus 3 times y plus 9, right? Equals 0. Makes sense? All right. And this means then that y is, this is a product of two things equals 0, then at least one of the factors is 0. So either this is 0 or the y plus 9 is the 0 guy. And that's equivalent to y is either 3 or negative 9, right? Agree with that? Okay. And then, how about we try, even though, look, even though we have equivalences all the way, it looks like it's not necessary to replace the y equals 3 and the y equals negative 9 in here to really check if we get a true statement. Let's check if y equals 3 gives us a good a tautology, a true statement. Okay, replace y by 3 here. Let's do it in some strange color. How about this? Replace y by 3, right? Replace y by 3 over here and over here. This is what then? Log base 3 of 3. And what's log base 3 of 3? Is 1, right? Is 1. And this is log base 3 of 9. 6 plus 3 is 9. What's log base 3 of 9? What's log base 3 of 9? Well, 9 is 3 squared. Correct? And if you apply this principle, this one, this power rule, right? The power goes down. Okay, if you can do it this way, or you know what? Let's use immediately the log base a of ax. Log base a with back to back with the exponential function of the same base. Back to back, you get only that number, right? They neutralize each other's action, you get back just 2. So this is how much? This is simply a 2. So that's a 2, and that's a 1. So 1 plus 2 is certainly 3. So y equals 3 gives us a tautology. So it's an acceptable solution. It is a solution, right? Okay. Now the other one, what's the other one? The other one is negative 9. If you plug in negative 9, what do we get? We get log base 3 of negative 9, and we're already seeing something wrong. Something is wrong with this. Log base 3 of negative 9, because log base 3 doesn't operate on non-positive number, negative 9 cannot be a solution. Negative 9 cannot be a solution. Make sense? So such a problem comes with its own provision. And the provision of the question is, which is the equation, is that the equation is meaningful. That's the provision. And when is this equation meaningful? It's meaningful when y is positive. For this guy to be meaningful, right? You need y to be positive, because if y is 0 or less, this becomes a non-meaningful entity. Remember, log base 3 or log base a doesn't operate on non-positive numbers. So y must be positive, and y plus 6 should also be positive for the second entity to make sense. And when is y plus 6 positive? This is when y is bigger than negative 6, right? When y is bigger than negative 6. So the provision of the question, it's an implicit condition. They're telling you already that y should be a positive number and y should be a number bigger than negative 6. For this guy to exist, y should be bigger than negative 6, and for this guy to exist, y should be bigger than 0. Correct? So under these assumptions, under this provision, then we can say that guy is equivalent to this guy, which is equivalent to ultimately the last part, right? So with this provision in mind, that's why we had, negative 9 didn't work even though we had equivalences. It looks weird, but the idea is If you keep this provision in mind, all of these are equivalent. Correct? All right. And since we're talking about this, what does this mean? Y being bigger than 0 and y being bigger than -6. I see some redundancy here. If you drop one of them, there is one if you drop is not going to change the story. And what's the thing that you can drop? Look, if you just ask y to be positive, aren't you already asking that y to be bigger than -6? Correct? So my point is, if you eliminate this request, are you losing any information? You're not, because asking y to be bigger than 0 is certainly asking also that y is bigger than -6. Make sense? So the provision of this question is that y should be bigger than 0, so the whole equation makes sense. So the idea is, whatever you find, the ones which do not satisfy this provision should be thrown away. In this case, that's the one that should be thrown away. Makes sense? Because I'm only asking y to be positive. Otherwise, the whole question doesn't make sense. Sounds good? All right, so when you solve such questions, keep in mind, either you find the provision a priori, and you check if your final answers verify, or your suggested solutions verify the provision. Whichever verifies the provision, you keep as a genuine solution. And if you don't want to go through this, if you don't want to find the provision of the question, no problem. Whatever you get here, keep in mind these are only suggested solutions. They are just the proposed ones. So check by hand each one in the initial equation. Whichever verifies the equation. In fact, both of them are going to verify it once it makes sense. Okay, so whichever of these suggested solutions do not provide a meaningful entity in the equation, this should be thrown away. Okay, and if it produces meaningful entities all the way throughout the equation, then that thing is certainly a solution. Okay, makes sense? So y equals -9 produces a non-meaningful entity here, so certainly I should throw it away. When you replace y by 3 here and by 3 here, both of these are going to make sense. You don't even need to check if they sum up to 3, because it's guaranteed via this analysis here. It's guaranteed to be a tautology once they make sense. Okay. All right. Let's keep going. Let's choose another one. How about a problem like this? Okay, this is similar to the one we just did. Maybe 56. ln x plus ln of x minus 3 equals ln of 5x minus 7. So 56. ln x plus ln of x minus 3 equals ln of 5x minus 7. Okay. All right, so how about condensing these two guys? We get ln of, this is the sum of ln's, sum of the logs. So this is the log of that common base of x times x minus 3. Again, these are properties. One of the properties that we developed in the previous section is equal to ln of 5x minus 7, right? Okay. So in this case, I have a logarithmic equation, but this is log base a acting on something and log base a acting on something else. If this guy and this guy are positive, then this is the same thing via double asterisk. If you remember double asterisk above, the same thing as saying that x times x minus 3, which is the input in this function ln, should match the input in this function ln, which is 5x minus 7. Agree with me? Okay. All right, this is also quadratic. So x squared minus 3x equals 5x minus 7, which means x squared minus 8x plus 7 equals 0. If you add 7 minus 5x to both sides, you should get this. Am I correct? All right. And if you want to factor this, you can use quadratic formula, or you can use some intuition. How can I factor this? Well, I can take x minus 7 and x minus 1, right? X minus 7 times x minus 1 is certainly x squared minus 8x plus 7. Okay. And as such, that's going to give you either x is 7 or x is 1. Yes? Either x is 7 or x is 1. All right. So as we said above, you either take each one by hand and you replace, or you develop the provision of the question. Since mostly you're gonna check by hand, I'm gonna do the provision. Okay. I'm gonna do the provision. So what's the provision of the question? The provision of this question is, I need each of these entities to be meaningful, right? For this guy to be meaningful, I need the input to be positive, right? So I need x to be positive for this guy to be meaningful. Over here, what do I need? What's the demand on x so that ln of x minus 3 becomes meaningful? X minus 3 should be positive, right? X minus 3 should be positive. The input in the log function should be positive. In this case, x minus 3 is the input. So x minus 3 positive means x bigger than 3. Correct? And finally, 5x minus 7 should be positive so that ln of that guy becomes a meaningful thing. And 5x minus 7 is positive provided x is bigger than 7 over 5. Agree with me? We got this. Okay. Well, for all of these, for this guy to be meaningful and this guy to be meaningful and this guy to be meaningful, this means that this has to work, this has to be verified, and this one has to be verified, and this one has to be verified. Yes? So all of these three inequalities have to be verified so that this equation is meaningful. All right, but certainly there is a redundancy here. Asking that x is bigger than 0 and x being bigger than 3 and x being bigger than 7 over 5. Let's do 2 at a time. How about the first two? Asking x being positive and being bigger than 3. If you eliminate this, are you losing it? If you eliminate this demand and you only ask for this, aren't you getting it for free? If you ask that x is being bigger than 3, aren't you already asking that x is positive? So you don't have to ask it twice in some sense, right? All right. If you ask that x is being bigger than 3, aren't you already also asking that x should be bigger than 7 over 5? 7 over 5 is less than 3, right? 7 over 5 is less than 3. Makes sense, because 7 is smaller than 15. Okay, so this guy is smaller than 3. If you ask that x is bigger than 3, you're already asking that x is bigger than this number. So you don't even need to request it. So long story short, the only demand that you need to ask is that x being bigger than 3. That's the provision of the question. Okay, so what I'm going to do is I'm going to just retain the one that's bigger than 3. Which one is bigger than 3? This is bigger than 3, but this is not. So this one is to be rejected, right? For those of you who did it by hand, checked by hand, plug in x equals 1. This is going to work, but you see here, you're going to realize that if you plug in 1 minus 3 is negative 2. ln of a negative number doesn't make sense. As such, you're going to realize that I need to throw it away. Okay, I understand that this is more work, but it tells you exactly when the question is meaningful. Okay, so if you want to understand the full story, that's the way to go. Okay, all right, so long story short, what's the solution set at the end of the day? The solution set is simply the singleton 7. Okay, I don't know if I forgot to write the solution set of the previous example. Yeah, I forgot. So the solution set here was at the time just 3, right? The singleton 3. Because we threw away the negative 9 at the time, right? Okay. All right. How about one more in the set? 58 is not that bad. Actually, 58 is very similar to 56. Okay, so we've done these kind of problems. How about I go somewhere else and do... How about 44? How about 44? 5 times log base 3 of 7 minus 5z plus 2 equals 17. Okay, so 44. So I have 5 times log base 3 of 7 minus 5z plus 2 is equal to 17. Okay, again, the question is to find all the z that do this job. Okay, so I'm gonna undo all the actions that are done on z. Let's first start by, as we used to, isolate the terms that are non-z terms with the z terms. So the non-z's, let's move them to the right side. The only non-z on the right side is 2, right? Let's move it to the right by subtracting by 2. So we get 5 times log base 3 of 7 minus 5z is equal to 17 minus 2 is simply 15. Correct? 17 minus 2 is simply 15. All right. Here I'm multiplying by 5. I want to undo the action that's done on 5. That's done on by 5. And such a thing as dividing by 5. If you divide by 5, you get log base 3 of 7 minus 5z is equal to, dividing by 5 forces this to disappear. Dividing here by 5 is 3, right? Okay. Don't forget, I'm after z. I'm undoing all the actions that are done on z. So far, the only actions that are done are multiplying by 5, subtracting by 5z, multiplying by negative 5, adding 7, and the last one here is letting log base 3 function act on 7 minus 5z, right? I want to undo them from the last one to the first one. So I want to undo obviously log base 3 first, and then I want to undo the action of adding by 7, and then I want to undo the action of multiplying by negative 5. So in the reversed order. Okay, so how can I undo the action of acting or letting log base 3 act on this entity? Who undoes the action of log base 3? It's the exponential function with base 3 that does it. Correct? So I'm gonna apply exponential function with base 3 to both sides. You can do it in a different way as we discussed above. Another way you can also rewrite this as you can rewrite this, right? You can rewrite 3 as 3 times log base 3 of 3. Correct? What am I saying here? I'm saying that you can also use this technique. Remember this technique? This guy, which was rewriting 3 as 3 times log base 3 of 3, and hence you can apply this principle and see this right hand side as simply log base 3 of 3 cubed. Correct? you can do it as such and continue exactly by applying double asterisk and keep going. What I'm going to do is I'm going to apply something similar to this bubble, correct? I'm going to apply something similar to this bubble. All right. So I'm going to erase this part. So I'm going to apply the exponential function. So I'm going to apply the exponential function with base 3 to both sides. Correct? I'm going to apply this. In other words, just apply asterisks. Just apply asterisk with this being x and this being y. X equals y is the same thing as a to power x is equal to a to power y, where a is chosen to be positive and different than 1 of your choice, and the a I'm going to choose is 3 to undo the action of log base 3, right? This is the idea. So as such, I get 3 log base 3 of 7 minus 5z is equal to 3 to power 3, right? So I'm applying the base 3 here. So let me color this in pink, say. So that's the exponential function I'm applying, right? So again, this is asterisk if you don't want to see it this way. I mean, they are asterisk, and this is the same with a being 3. So I'm applying, so this is x equals y. Asterisk tells us, well, a to power x is the same as a to power y. As long as you choose a to be positive and different than 1, you're allowed to choose any such base. I chose 3, so that now look, back to back exponential function with the base 3 with back to back with the logarithmic function with base 3, same base. So neutral action. As such, we simply get 7 minus 5z is equal to that number, which is 27, right? Okay, and then if you solve for z, that's not bad. This is negative 5z is equal to 20, which means z is equal to negative 4, right? Correct. All right, and as we talked about that, I mean, every problem that involves logarithmic functions comes with its own provision. And what's the provision here? Again, same thing. If you don't want to deal with that, you can just plug in the negative 4 in the z spot and check if you don't even to check again. You don't even to check that they produce the same entity both sides. But the only thing that you need to check is that log base 3 acting on this number with this particular choice of z comes out as a meaningful entity. And once it's meaningful, it's guaranteed to work. All right, so if you want to go the provision route, so what's the provision of the question here? The provision is that this entity is positive, right? The only demand on z is that this entity is positive, because if it's not positive, log base 3 of that entity is not meaningful, right? So the only provision is that this guy is positive, which means that z is smaller than 7 over 5. Am I correct? All right, so z is smaller than 7 over 5. Such as z only works it provides a meaningful equation, and certainly this z is smaller than 7 over 5 because it's negative altogether. As such, I'm going to accept it. I'm going to accept that z. Certainly it's going to work. I don't even need to check. So therefore, the solution set is the singleton negative 4. Okay. All right. Next one. Okay, so let's move on to the next set of problems here. All right, how about these problems? 87 through 94. find an equation for the inverse function. For the inverse function, let's do one of them. How about we do 94? Okay. So 94. I have f of x equals log base 10, right? Whenever you don't write the base, it means the base is 10, x minus 11 plus 8. So I want to find the inverse function. Certainly the inverse here exists because, look, log is a one-to-one function. It passes the horizontal line test. You shifted 11 units to the what here? To the right, correct? So it's still one-to-one, and then you shift the whole thing, you shifted vertically upward 8 units. What used to be one-to-one with a couple of horizontal and with one vertical shift and another horizontal shift, that's gonna give you still a one-to-one function. As such, f inverse is gonna exist because the function f is one-to-one. Okay, you don't have to check this, but it's part of the question because they ask you to find the inverse function. I'm just highlighting why this is the case. All right. So how did we use to find the inverse function? So this is the same as saying that y is log base x minus 11 plus 8, right? So what we used to do is we used to have if y is equal to f of x, that's exactly the same as saying that x is equal to f inverse of y. Am I correct? That's the engine behind finding the inverse function. So if you have y in function of x, if you have y solved for x as such here, right? You have y on one side and x on the other side. And if you manage to solve for x, then the right hand side, that guy is gonna be certainly f inverse of y. This is what we used to do, if you remember. Okay. Well, let's do it. I want to solve for x. So this is the same thing as saying that y minus 8 is log base 10 of x minus 11. I'm solving for x, right? Let's undo the action of log base 10. How can I undo the action of log base 10? Again, there are a couple of techniques. We've introduced them above. You get to choose. What I'm gonna choose, I'm gonna apply the exponential function with this base 10 to both sides. Okay, I'm gonna apply the exponential function with base 10 to both sides, right? Which means I'm using asterisk. I'm using asterisk. That's gonna be the x in asterisk, and that's gonna be the y in asterisk. And the base I'm choosing is 10. Remember, I can get to choose any base I want as long as the base is positive and different than 1. The base 10 I'm choosing to undo the action of log because I'm trying to free all the actions that are done on x. Okay. So as such, I get 10 to power y minus 8. I'm applying the exponential function with base 10. So I get 10 to this power equals 10 to that power log base 10 of x minus 11, right? Now what is that? 10 exponential function with base a back to back with log function base a. I mean, that was specialized to be as such anyway, right? Back to back, neutral action left over is x minus 11. You get 10 to power y minus 8 is equal to x minus 11. And this means that x is, if you add 11 to both sides, you get 10 to power y minus 8 plus 11. Agree with me? So based on this discussion that we used to have, once we solve for x, we've got the f inverse acting on the input y. So that guy, that's the f inverse acting on the input y. Makes sense? Now, as we used to say, if your preferred choice of the input to be x, replace x by y, and just whatever sits here is gonna sit here, right? So get f inverse of that input, your favorite letter, whatever it is, maybe t, z, s, whatever. It's gonna be 10 to the power, that variable that you chose, let's say t minus 8 plus 11. Make sense? Okay. All right, let's keep going. Let's go to page 420. It shows one of these problems from 95 to 112. Still very much close to what we used to do. Solve the equation, one of these. Okay, this looks a little strange. How about 108? Let's do 108. So 7 times ln, absolute value of ln x minus 14 equals 0. Remember, the question is to find the solution set. Okay. So this is problem 108. 7 times ln of absolute value of x. Sorry, it's the other way. It's the absolute value of ln x minus 14 equals 0. Correct? And the question is find the x that does the job, or find the x's that do the job. Okay. Well, 7 times something minus 14 is equal to 0. That's the same thing as 7 times the thing equals 14, which means that the thing is equal to 2, right? 14 divided by 7. Correct? So down to this. All right. And this is something we've talked about before. What's the absolute value of a equals a non-negative number? If b is non-negative, what's the absolute value of a equals to that non-negative number? That's equivalent to saying that a is plus or minus that number b, right? Agree with me? So we talked about this before. So what we get is that ln x, that's playing the role of a here, obviously it's the guy between the bars, is equal to plus or minus 2. And plus or minus 2, let's write it as two equations, so either negative 2 or plus 2, right? Now you can solve it the way you want. You want to solve for x. What I'm going to do is I'm going to apply the exponential function with base e to both sides to clear that ln. I want to undo the action of ln, so free the x. And if you apply the exponential function with base e here, it undoes the action of ln. Or if you wish, you can also do it the other way that I talked about above. You can multiply by ln e here, because ln e is 1, right? And bring that negative 2 as an exponent. Bring that negative 2 as an exponent here. And then this becomes ln x equals ln of e to power negative 2. And double asterisk tells you that x must be e to power negative 2. And similarly here. Okay? I'm not going to do it this way. I'm going to do it as I just said before. I'm going to apply exponential function with base e to both sides. You get to choose your own approach. They're all correct. So I'm applying the exponential function with base e to both sides to undo the action of ln. And that's going to give me e to power negative 2 here. Or if you apply the same thing, e ln x is going to be e squared, right? And now what's e to power ln? So what's exponential function with base e back to back with the logarithmic function with base e? Back to back, neutral action, so you get x equals e to power negative 2. What's e to power negative 2, by the way? This is the reciprocal of e squared. This is the reciprocal of e squared. Or similarly here, back to back, these two functions, they are inverses, so you get x equals e squared. Correct? So these are the only two guys that do the job. And what's the provision of this question? What's the provision of this question? Well, the provision of this question is that x is not non-positive, right? So the only request on x is that x to be positive, correct? So provision x is positive. Why I need x to be positive? Because look, ln is acting on x. If x is not positive, which means 0 or less, then this is not meaningful. As such, the whole thing is not going to be a meaningful question. All right, which one of these is not positive? Well, this is certainly a positive. This is the reciprocal of a positive number. This is positive and this is positive. So both of them are positive. As such, I'm going to accept both of them. These are going to be both my solutions to this equation, 108. Makes sense? So I'm going to get the solution set is simply what? Is simply 1 over e squared and e squared. Okay. All right, so this is the end of this section.